Hello, today we will continue to discuss descriptive statistics, numerical measures. We will discuss measures of distribution shape, relative location, and detecting outliers. We will also discuss 5 number summaries, box plots, and we will discuss measures of association between two variables, covariance and correlation coefficient, measures of linear association between two variables. So we will discuss distribution shape, which is skewness, z-scores, Chebyshev's theorem. We will discuss how to detect outliers. You can numerically calculate the skewness using this formula, but you will not be responsible from using this formula during the exam. You will have some multiple choice questions from skewness, such as if the skewness is 0, if distribution is symmetric, then skewness is 0. If it is symmetric, so the left half is the mirror image of the right half. You can have left skewed or negatively skewed, or you can have right skewed, or you can say positively skewed histograms. Left skewed means that you have longer left tail, so left tail extends to the left, which is also called negatively skewed. But this is not highly skewed. You don't have very long left tail here. This is moderately skewed left. So then the skewness is less than 1, which is negative 0.31. You can have positively skewed histograms or right skewed histograms. So this is positively skewed. You have a longer right tail, but it is not very long, so it is moderately skewed. Usually it is considered highly skewed if the skewness is larger than 1. So in this case you have very long right tail, so skewness, this is considered highly skewed right. Now for this example, this is the histogram, this is also right skewed. Skewness is 0.92 here. So then for a symmetric distribution, the mean and the median are equal. So you can have right skewed or left skewed distributions. Z-scores are the measure of relative location. So in addition to measures of location, variability, and shape, we are also interested in the relative location of values within a data set. Measures of relative location help us determine how far a particular value is from the mean. So you need to know the mean and the standard deviation to calculate the measure of relative location. If we know the mean and the standard deviation, we can easily determine the relative location of any observation. So these are also called the z-scores. So measure of relative location is also called the z-score. How do we calculate the z-score? Which is, for any observation, it is xi is the observation minus the mean, sample mean, divided by the standard deviation, which gives us the number of standard deviations, the data value is away from the mean, which is xi is away from the mean. You can have negative z-score, positive z-score, or 0 z-scores. If z-score is 0, this means that value is equal to the sample mean. If z-score is negative, then that value is less than the sample mean. If z-score is positive, then that data value is larger than the sample mean. So we can have 0 z-score, positive z-score, or the negative z-score. It gives the number of standard deviations that value is away from the mean. Here we see the z-scores. One application of z-score is to determine the outliers. If you have a z-score less than -3 or larger than +3, that might consider an outlier. Here the most extreme z-scores are -1.2 and 2.27. So here we don't have any outliers. So let's see one example. So we have exercise 46, 54, 42, 46, 32. In this example, sample mean is, so we need to calculate the sample mean first. This example, sample mean is .44, and the standard deviation is 8. So we need to know the mean and the standard deviation. Yeah, it is 8. Now what do we need to do? Ci equals xi or x bar over s. So we can find xi minus x bars. So 46 minus 44, 2, 54 minus 44, 10, 42 minus 44, -2, 46 minus 44, 32 minus 44, -12. Now we divide this by the standard deviation, which is 8. Which is 2 over 8.25. 10 over 8, 1.25. -2 over 8, -0.25. -12 over 8, -1.5. So this means, how do you interpret the z-scores? This means 46 is 0.25 standard deviation to the right of the mean, because it is positive, so larger than the mean. 54 is 1.25 standard deviation to the right of the mean. 42 is 0.25 standard deviations to the left of the mean. 32 is 1.5 standard deviations to the left of the mean, which is the measure of the relative location. Gives us the number of standard deviations, that values away from the mean. We can use these scores to detect outliers. If you have a z-score larger than 3, might be considered an outlier. If you have a z-score less than -3, might also be considered an outlier. Other application of the z-score is the Chebyshev's theorem. This states that Chebyshev's theorem states that at least 1 minus 1 over z-square of the data values must be within z standard deviation of the mean. Such as if z is 2, 1 minus 1 over 2 squared which is 0.75, This means at least 75% data values. So here if z is 2, must be within 2 standard deviations of the mean. Here z doesn't need to be an integer, but it needs to be larger than 1, because if z is 1, then this is 0. it needs to be larger than 1. So at least 75% of the, based on the Chebyshev's theorem, at least 75% of the data values must be within 2 standard deviations of the mean. At least 89% of the values must be within 3 standard deviations of the mean. At least 94% of the values must be within 4 standard deviations of the mean. If we look at the apartment rent, say z is 1.5. That is 1 minus 1 over 1.5 square so then it will 1 minus 1 over 1.5 square, which is 0.56. This means 56% of the rent values must be within 1.5 standard deviation of the mean. So what is 1.5 standard deviation? X bar minus 1.5 times the standard deviation. Here x bar is 590.8 minus 1.5, standard deviation 54.74, which is 509. X bar plus 1.5 standard deviation, so 590.8 plus 1.5, which is 673. So then based on this theorem, at least 56% of the values must be between 509 and 673. And if you look at the data, actually 86% of the data values are between 509 and 673. So this provides some lower bounds. It says it is 56%. We can also use this score, like we mentioned before, to detect the outliers. What's an outlier? Unusually large or unusually small value in a data set. We always wish to detect the outliers because an outlier might be an incorrectly recorded data value. If that's the case, we need to correct it. Or it might be a data value that was incorrectly included in the data set. For example, you meant to write 30, but accidentally you put one more zero and wrote it 300. So which is incorrectly this is incorrectly recorded, which in this case you need to correct it. Or you may have incorrectly included data value, such as you accidentally type some value which doesn't belong to the data set. In that case, you need to remove it. If it is incorrectly included in the data set, then you need to remove it from the data set. Or it might be a correctly recorded data value that belongs in the data set. If that's the case, that should stay in the data set. So we always wish to detect the outliers. Here, we look at the z-scores. These are the most extreme z-scores, which is negative 1.2 and 2.27. So there are no outliers in this data set. Now we will discuss 5 number summaries and box plots. So previously we discussed some graphical displays, but 5 number summaries, and you can use a box plot to quickly summarize large quantities of data. So the box plots based on the 5 number summaries. What are the 5 number summaries? Smallest value, first quartile, median, third quartile, and largest value. So we can use the box plots to quickly summarize large quantities of the data. Now here the 5 number summary, so the smallest value, so minimum value 525. First quartile 545, medium 575, third quartile 625, and the largest value 750. This is the 5 number summary. Smallest, first quartile, median, third quartile, and the largest value. Now how do we obtain the box plot? So this is the range of the values. You can draw this vertically or horizontally. Just 4. Then we locate the median, 575. Draw a line, vertical line. First quartile 545. Third quartile is 625. And then we combine them as a rectangular box. Now we will draw the whiskers, but first we will determine the lower and upper limit for the outliers. Box plots are frequently used to detect outliers. How do we determine the lower limit for outlier? First quartile minus 1.5 times interquartile range. What's an interquartile range here? Third quartile minus the first quartile. So then the third quartile minus the first quartile. Which is 80. So then the first quartile 545 minus 1.5 times 80 . 425. This is the lower limit, so this means if we have a value less than 425, it is considered an outlier. And the upper limit, third quartile plus 1.5 times interquartile range. Third quartile is 625 plus 1.5 times 80. 745. So if we have a value larger than 745, it is considered an outlier. If we have a value less than 425, it is also considered an outlier. So then 425 here, 745. Do we have any outliers? No, because our largest value is 715, smallest 525. So we don't have an outlier, so then we draw the whiskers. whiskers goes to the smallest and the largest value inside the limit. So smallest value 525. This is wrong. So 525. Whisker is a dashed line. And the largest value is 715. Inside the limit, so we don't have any outliers. Box plots also provide another way to provide outliers. Here you see the first quartile, median, and the third quartile. Then we combine them as a box. Then we determine the limits for outlier. We use the interquartile range, which is third quartile minus the first quartile. So if all the values are inside the limits, then we don't have any outliers. If we have data values, if we have data outside these limits, they are considered an outlier, and the location of each outlier is shown with this asterisk. Now the lower limit 425 and the largest limit 745. So the lower limit first quartile minus 1.5 times interquartile range, which is 425, and the upper limit third quartile plus 1.5 times interquartile, which is 745. So we don't have any outliers in the apartment rent data. So whiskers goes to the largest and the smallest value inside the limits. So it goes to 525 and 715. If you had outliers, then you show it with asterisks, like this. But here we don't have any outliers. Now we will discuss the measures of association between two variables, which covariance and the correlation coefficient. These are the numerical measures of association, linear association between two variables. So we have examined numerical methods used to summarize the data for one variable at a time. But often we are interested in the relationship between two variables. So the covariance and the correlation coefficients are the numerical measures of association between two variables. So covariance is a measure of linear association between two variables. Positive values indicate a positive relationship, and negative values indicate a negative relationship. How do we calculate the covariance for samples? Sum of xi minus x bar. Now remember, we have two variables, so we calculate the sample mean for each variable, and then we subtract the mean from each variable. So xi minus x bar times yi minus y bar, and we add those up divided by n minus 1. So we subtract the mean for each value of xi, and we subtract the mean of y for each value of y, multiply those, and then add them up. So it might appear that a large positive value for a covariance indicates a strong positive linear relationship, and that large negative value indicates a strong negative linear relationship. But one problem with using covariance as a measure of the strength of the linear relationship is that the covariance depends on the units of the measurement. So if we change the units, then the value of the covariance changes. The sign doesn't change, but the value changes. For example, relationship between height and weight. Then you can measure the height in terms of inches or in terms of centimeter, then the value changes. Or you can measure height in terms of you can measure weight in terms of pounds, kilograms, value changes. So with height measured in inches, you can measure height in inches or feet. If you measure the height with inches, then you obtain a larger value for the numerator in the equation. and then there you have larger covariance. But in fact, the relationship doesn't change. So measure of relationship shouldn't affect by the units of the measurement. So then we have another measure of relationship between two variables which is not affected by the units of the measurements, which is correlation coefficient. Correlation coefficient is unitless, it's not affected by the units. So we cannot use the covariance to comment on the strength of the relationship because the covariance depends on the units of the measurement. That's why we also calculate the correlation coefficient, which is unitless, it's not affected by the units of the measurement. So correlation is a measure of linear association and does not necessarily the causation. Just because two variables are highly correlated doesn't mean that one variable is cause of the other. For example, we may find that the quality rating and the typical meal price of restaurant are positively correlated, but simply increasing the meal price will not cause the quality rating to increase. And to calculate the correlation coefficient, we have to calculate covariance first. Sx and Sy are the standard deviations of the variables. So you calculate the covariance and standard deviation of each variable. So the correlation coefficient is covariance divided by the standard deviation of the variables. We have two variables here. Covariance can take any numeric value, but the correlation coefficient can take on values only between -1 and +1. Values near -1 indicate a strong negative linear relationship, and the values near +1 indicate a strong positive linear relationship. Closer the correlation is to 0, the weaker the relationship. If it is +1, it's a perfect linear relationship, perfect positive linear relationship. If it is -1, it's a perfect negative linear relationship. Closer to 0, the weaker the relationship. Now let's look at one example. We have xi and yi values. Now we will see how to calculate the covariance and correlation coefficient. Now we have to calculate the x bar, which is sum of xi over n. Here these are the paired values. So here n is 3, sample size is 3. So then what is this x bar, which is 10. We have two variables x and y. So the sample size is not 10, it is 3 because these are the paired values. Sum of yi over n, which is average of these values is 30. Sxy is sum of xi minus x bar, yi minus y bar, over n minus 1. Now which means we have to subtract the mean x bar from each xi value. So then 5 minus 10, -5, 10 minus 10, 0, 5. Now yi minus y bar -30, -20, 0, 20. So now we multiply these. Times yi minus y bar. So then negative 5 times negative 20, which is positive 100. Zero times 0, 0. 5 times 20, 100. Now what do we need to do? We have summation here, so we add these up, which is 200. N is 3. This is 100. 200 divided by 2 is 100. This is the covariance. How can we interpret this covariance? It is positive, so positive values of covariance indicate a positive relationship. But to comment on the strength of the relationship, we have to calculate correlation coefficient, which is Rxy, which is covariance divided by standard deviations of the variables. How do we calculate the standard deviation? Square root of the variance, sum of xi minus x bar square divided by n minus 1. Same thing for sy. Now we use the y values, yi minus y bar. So we have two variables, so we calculate the mean and the standard deviations for both variables. We already calculated xi minus x bars and yi minus y bars. To calculate the standard deviation, we can simply square these. So then this is equal to divided by 2 square root of 25, which is just 5. Now same thing for yi minus y bar square. So we already have yi minus y bars. We square those. Negative 20 square 400, 0, 400. That is 800 divided by 2, which is square root of 400, which is 20. Now we can simply calculate correlation coefficient, which is covariance 100 divided by the standard deviations of the variable. It is 1. It is plus 1, so this means a perfect positive linear relationship. So if covariance is 1, if covariance is positive, then correlation coefficient is positive also, because standard deviations can never be negative. If covariance is negative, since standard deviation can never be negative, correlation coefficient is also negative. So values near positive 1 indicates a strong positive linear relationship. Values near negative 1 indicates strong negative linear relationship. Covariance can take any value, but correlation coefficient is always between negative 1 and positive 1. This is another example. So a golfer is interested in investigating a relationship, if any, between driving distance and 18-hole score. Now x is the driving distance, y is the 18-hole score. So you can create a table like this to do the calculations. First, you find the averages and the standard deviations of each variable. We have two variables, x and y. X bar is 267, Y bar 70. Standard deviation of X is 8.2192 and standard deviation of Y is 0.8944. Then you subtract the mean from each X value. You subtract 267, so 277 minus 277.6 minus 267. You do it for each of them. And then you subtract the Y bar from each Y value, so 69 minus 70, negative 1, 71 minus 71. You do it for each of them. And then you multiply those, so 10.65 times negative 1, negative 10.65, negative 7.45 times 1, negative 7.45, 2.15 times 0, 0, this is 0, negative 11.35, and negative 5.95. So the total of this column is negative 35.4. So then the numerator, negative 35.4 divided by n minus 1, n is 7. 1, 2, 3, 4, 5, n is 6. 6 minus 1. So this is a covariance, negative 7.08, which indicates a negative relationship. Now we also calculate the sample correlation coefficient to see the strength of the relationship, which is covariance divided by the standard deviations of the variables, which is negative 0.9631, which indicates a strong negative linear relationship.